We'll shift now to English, and our next speaker will be Marie Carrière from Grenoble, next to here. And she will talk about safer by design indium phosphide quantum dots. Marie?
Yes. Okay, so in the laboratory, we try to develop some safer by design indium phosphide quantum dots. So I'm in a laboratory called SIMS in Grenoble in France, which is a very multidisciplinary laboratory where we do both chemistry, physics, and biology. And personally, I am a toxicologist, so I mainly do some biology. So quantum dots are colloidal semiconductor nanocrystals that show very nice properties, especially they are brightly fluorescent, and we can monitor and manage their fluorescence by. Do you see my pointer?
Yeah, it's okay. It's okay.
Okay, so you can change their optical properties by changing their size and their composition. At the moment, they are used in some light-emitting diodes and in some TVs, screens, displays, etc., because they enhance the quality of the colors. But the drawback of these quantum dots is that at the moment, most of the quantum dots on the market are made of cadmium selenide, and this element, especially cadmium, is highly toxic. It is carcinogenic. These QDs are made of chemical elements that show low abundance in the earth crust, and at the moment there is no recycling solution for these QDs. And so their use, due to their toxicity, their use is now very limited, at least in the European Union, via the RoHS directive. And so we need to develop some alternative quantum dots. And in this search for alternative quantum dots, the best candidate at the moment is indium phosphide. And so a little bit less than 10 years ago, we developed a strategy to synthesize some indium phosphide quantum dot by using a safer by design approach. The idea is that we want to have to think the quantum dot from the very first step of its development for it to be safer. So we built our strategy on 3 pillars. The first one is the replacement of cadmium by indium. It also enhanced the stability of the core, so it is good also for the property of the QD. The second pillar is the reduction of the content of indium in the core of the QD, and so we alloy this core with some zinc, selenium, gallium, which are less toxic elements. And then the third pillar is to try to limit the release of indium from the core of the QD, and to do so, we coat the core with a shell made of selenium sulfur and zinc sulfur and zinc selenide. And so what is also important is not only to focus on the pristine quantum dot, the quantum dot that is produced in the laboratory, but also to look at the toxicity and the degradation of the quantum dot during its life cycle. And so we studied the physicochemical characterization and the toxicity both of the pristine QDs, but also after aging in environmental condition using a climatic chamber. So very briefly, the synthesis of these QDs, they are synthesized based on indium myristate zinc stearate, and this permits to synthesize the core, indium phosphorus and zinc, or indium phosphorus, zinc, and sulfur. Then we coat this core with a gradient shell made of zinc, selenium, and sulfur. And then what we also did is to further coat this first shell with a second shell made of zinc sulfur, either thin or thick. And so with these 3 QDs, the gradient shell, the thin shell, and the thick shell, we looked at their degradation in environmental conditions and at their toxicity. First of all, their physicochemical transformation. We age them in a climatic chamber for 15 minutes to 360 minutes and looked at the fluorescence of the QD, because as soon as the fluorescence fades, it means that the QD is degraded. With the gradient shell, we see that after only 15 minutes, there is no more fluorescence, so the QD is totally degraded. With the thin shell, after 45 minutes, we still have some fluorescence. So here we have a first proof that the double shell QDs are much more robust than the gradient shell QDs. And with the thick shell, after 60 minutes, we still have fluorescence. So the thick shell is also more robust than the thin shell QD. And so it is more interesting from a safer by design point of view, because if it degrades less, then the fluorescence will stay longer. During this physicochemical transformation, what we observe, so you have here some cryo-TEM image of the pristine QDs. They have a core of around 3 nanometers, and then their total size is around 4 to 6 nanometers, depending on the type of shell. And after aging, what we see is some very, very large precipitates that are very heterogeneous, and their EDX analysis shows that indium, zinc, phosphorus, and oxygen, it is the red region, number one, co-precipitate. Then we have some co-precipitation of zinc with phosphorus and oxygen, and then some co-precipitation of selenium and sulfur. So after aging in environmental condition, we don't have some quantum dots anymore. We have this very large and heterogeneous precipitates. When we expose some cells, and here it is a model of the skin, we used human primary keratinocytes. When we expose the cells to quantum dots, both pristine and aged, we see some quantum dots entering inside the cells and distributing in the cytoplasm in some vesicles. We never saw any quantum dots in the cell nucleus or in any organelle. So on the left side, you have cells exposed to the pristine ones. On the right side, cells exposed to aged quantum dots. And what we observed in terms of toxicity is that the pristine quantum dots show very low toxicity. You have here a presentation of the percentage of viable cells after exposure to increasing concentrations of the quantum dots, either the thick in white, the thin in dark gray, or the gradient shell in light gray. The gradient shell is a little bit more toxic than the other ones, because when we expose the cells at 100 nanomolar, it induces the death of around 50% of the cell population. But after exposure to the aged QDs, we have a much more important toxicity with significant cell death as soon as after exposure to 6 or 12 nanomolar of the aged QDs, and whatever their composition. So as a conclusion, we have a safer by design strategy. It is successful because we see that the double shell QDs are more resistant to environmental aging than the single shell QDs, but still our strategy at the moment is not optimal because the aged QDs are still quite toxic. The toxicity is related to aging, and aging is related to QD dissolution and the release of some indium and zinc ions that precipitate. And so at the moment, we are testing some new formulations with new shells. We had the idea of further coating the QDs with an aluminum shell. We try also to reduce the zinc content because we saw some toxicity of zinc in these QDs. And we still work on alternative composition, alloying with gallium, etc. And that's all. I would like to thank you for your attention, thank all the funders of this work and all the people that participated.
So thank you very much, Marie. One question from Alain Ibanez. What about the preparation method? Is it a typical rapid hot injection?
Okay, so I'm not a chemist. I don't know the details. What I saw in the articles is that it's a one-pot synthesis, and what I know from what chemists told me, yes, it is a rapid injection, hot injection. These QDs are synthesized by Peter Reis in the laboratory. Maybe you know him, Alain.
And another question, how much time you need of incubation in order to make the QDs enter the cells?
Sorry, I didn't understand.
How much time do you need for the QDs to enter the cells? How much time of incubation?
So yeah, the images that I show you were after 24 hours of exposure. Typically after 4 hours, I think that we have no QDs inside the cells, but it increases with the time. I think that around 12 hours, we should have some QDs inside the cells.
Okay, thank you very much. I think there will be more questions on the chat.
Okay.